Hello calculus fans, welcome to section 10.3 where we learn all about polar coordinates. You'll notice for this section I don't have a handout, so this one we're going to have to take notes the old-fashioned way. Hopefully you can remember how to do that with some paper and some writing. So we start off just talking about a quick review of, well, not really even a review, but let's talk about two-dimensional coordinate systems. Okay, so we've got these coordinate systems, and we're very familiar with one of them. The coordinate systems for 2 dimensions. One of them is a Cartesian coordinate system, or sometimes called the rectangular coordinate system. Cartesian, after René Descartes, who did a lot with analytic geometry. So he took geometric figures and put them on a coordinate system where then you could talk about them analytically. Okay, so this Cartesian coordinate system or the rectangular coordinate system, same thing. And these are familiar x, y coordinates, right? So there'd be something like, what we do, we've been doing for a long time. Got this point out here, x, y. So we go out x units, go up y units. And even when we use parametric equations, so in 10.2 we use parametric equations and they use the same system, but here we would call it x and y would be functions of t, right? So we had f of t and g of t. So so this was the parametric. When we're using parametric equations, they still use the Cartesian coordinate system. So the one we're going to look at today, though, is the polar coordinate system. And this one doesn't use x and y, it uses r and theta. So the way this one would work, if we're going to identify that same point, with a polar coordinate system, you do something different. You say, okay, what we're going to do, we're going to start in this standard position here, and we're going to open this angle up theta degrees. And then we're going to go out r units. And so you describe, let me get that out of there. Okay. You describe this angle and this distance to get to that point. And then you use r, the point would be labeled r theta. Okay, so that's what we're going to look at today. So some of the terminology you'll see, where we're used to calling this right there the origin. When you use polar coordinates, you're going to call this the pole. And where we call this the x-axis, when you use polar coordinates, you'll call this one the polar axis. At least for the positive x, you'll call this the polar axis. Let's take a look at these polar coordinates and kind of get a feel for how they work, because they're definitely a little different. They're a little different than the Cartesian coordinate system. So for our first example, let's consider this point 3 and 2 pi over 3. So we've got our typical two-dimensional plane here. And what we're going to say is we're always going to start in standard position here along the x-axis, or what we'll now call the polar axis. And the angle is going to go, a positive angle will open counterclockwise. So they're going to go up this way. That's a positive angle counterclockwise. Now this one's going to go 2 pi over 3. So it's going to start here and go up 2 pi over 3. So pi over 3, of course, is 60 degrees. So you got and plus we're sort of used to using angles measured in pi over 3 radians, right? So you have pi over 3 would be here. 2 pi over 3 is another 60 degrees, so it'd be 120 degrees. Of course, 3 pi over 3 would be the same as pi. So if you open up an angle all the way, it's pi. So basically we got 1 pi over 3 and then 2 pi over 3. So this angle would go over like this. It'd be 2 pi over 3. It's going up here. So this angle here is 2 pi over 3. And then it's going out 3 units. So you could think of it like 1, 2, 3 units. So there, right there is the point P. Right, so 2 pi over 3 is the angle and 3 units out, so that's how we would write that one. Okay, what about if we've got another one? Let's say example 2. Let's say for this one we've got this point Q and it is -2 and 70 degrees. Okay, so we start again, we'll always start standard position here. And 70 degrees, it's positive, so we're just going degrees, which is okay. We can use radians or degrees. 70 degrees, positive, so we go this way counterclockwise. 70 degrees, which would make we'd have a line coming out here, but in this case, right, so this is 70 degrees. In this case, the 2 is negative, so we're not coming out this way 2, we're going back. We're going backward 2. So we're going to have this line extend back here. And it's probably a little short of 70 degrees, but you get the idea. But this goes up 70 degrees. This -2 makes it come back this way 2. So we come out here 1, 2, and that point right there is the point Q. Now you might notice something about this. You might think, well, what about this? Couldn't I just start here and go all the way over here and then have a +2? And yes, you could. This is one of the big differences between polar coordinates and Cartesian coordinates. Cartesian coordinates are unique. So what that means is if you've got a Cartesian coordinate and it's like, let's see, 1, 2, 3, 1. This point 3, 1 is a Cartesian coordinate. That's the only way to label that point. Right? It's 3, 1. There's no other way to say it. But we're going to find out with polar coordinates, they're not unique. So I could call this -270, or what else could I call it? Like, if I start here and go all the way around here, isn't that just 70 degrees plus another 180 degrees, right? A straight line, 180 degrees. So instead, if I start here and go all the way around here, that's just 70 degrees plus 180 degrees. So that's just going to be 250 degrees. And both of these describe this same point Q. So polar coordinates are not unique. Cartesian coordinates are unique. There's only one way to describe this. But here's the takeaway. This is going to be important for us to know. Polar coordinates are not unique. In fact, there's an infinite number of ways to describe this point, because couldn't I get here and then just add 360 degrees and get here and add 360, 360? You could just keep adding 360, right? So there's an infinite number of ways to do this. So in the homework, sometimes what they'll ask us is to describe this point using a positive r and also a negative r. Okay. So, all right, let me make some room here for the next one. Let's look at example 3. I guess I'll slide this one in here, example 3. Let's make example 3 be point R. We'll call point R -4, -7 pi over 6. Okay, so with this one, let's have you try this one out. Okay, so press pause. You got to really do it, though. You got to try it. Don't just wait for me. Press pause, try it out, and see what you come up with. Okay, so hopefully you press pause. And hopefully while it was paused, you figured this out. And you're thinking, okay, I'm going negative in the negative direction. So if I'm starting from standard position, this time I'm going clockwise. I'm going down here, right? 7 pi over 6. Well, 6 pi over 6 is 1 pi, right? So 6 pi over 6 would get me here. I go 1 more pi over 6. And of course, pi over 6 is 30 degrees, right? So I'm basically going to come up here, something like this. So this direction here, this angle is negative 7 pi over 6. Again, every time you have a positive angle, you're going counterclockwise from standard position. Negative angle, you're going clockwise from standard position. And then we go out negative 4. Okay, well here we go with that negative again. If this said positive 4, I'd come out here 4 units. But it's negative 4, so I'm going back here 4 units. So I need to go back here 4 units. So let's say we've got 1, 2, 3, 4. And there is the point R. Okay, but let's just practice. What if we wanted to have a positive 4? What could we put there? And there's more than one answer, of course, but to get a positive 4, well, you could just do this. Couldn't you just start here and go negative? This is basically pi over 6 here, right? Because you went up here. This is pi over 6 here, so it means this is pi over 6. So I could just go negative pi over 6. Start from here, go negative pi over 6, that would get you to here and go out 4. But what about this? What if I wanted to have both of these be positive? I want a positive 4 and a positive angle. So in other words, I want to start here in center position, go around a positive amount to get here. So what would this angle be? If I go from here and go all the way around to here, well, just think this is pi over 6 right here, right? If I went all the way around, I'd go 2 pi, which would be like 12 pi over 6. So I'm just pi over 6 short of that, which means that would be 11 pi over 6. Okay, so hopefully that makes sense. This little introduction to it. And then I'm going to show you something that many of you will see, because a lot of you are going to end up taking Calculus 3. In Calculus 3, you're going to study 3-dimensional coordinate systems, and 2 of these are just extensions of polar, so I'm just going to give you a quick jump start on those. But before we do that, just remember the takeaway here: polar coordinates are not unique. Cartesian coordinates are. All right, so let's take a look and see. We'll just look real quick. This is not in 10.3, but it's something you're going to see, and it's related to what we're doing, so just give you a jump start on here. Let's talk about coordinate systems. But this time 3-dimensional. Okay, so we'll just look at these real quick, okay? So the one that's going to be the easiest to make sense of is just the Cartesian. So look at the Cartesian coordinate system. Now this time there's going to be x, y, and now a z. So if you think of it like whatever room you're in, look right in the corner. This is one wall along the floor, this is another wall along the floor, then you've got the little corner going up. So just think of the bottom as the xy plane like we're used to using. And then we just add one more dimension. Okay, so we have to have space, so 3-dimensional space, so we need this other dimension here. So the way this works with a 3-dimensional Cartesian system, it's pretty much what you would expect. So you could come out here along the x-axis, come out here along the y-axis. So let's say you come out to this point here. You come out here. Then you just go up. Right, so this would be your point x, y, z. This would be probably the most familiar one because it's just like the 2-dimensional system with one more coordinate, right, x, y, z. So that gives you the 3rd dimension. So that'll be the most common, or the most probably intuitive one. The other 2 are cylindrical and spherical, and they're both extensions of polar. Okay, so these inputs, now both of these are extensions of polar, which you'll see. This has r, theta, and z. This is just like it'll be polar down here with a z. Then spherical is a little different. You have rho, theta, and phi. So cylindrical will be like what we talked about before. So we'll have maybe something that comes out here. So this will be theta coming out from the x-axis. So let me just label these so it's a little easier to deal with. So if we think of the x-axis here, so theta will come out here, and then this length of this is r, and then from the end of this will come straight up, and then that will give us this distance here is z. So this distance here would be z. So then we have r theta z. So it's just a different way to describe how to get to this point. All right, same with this, just a different way to get to that point. This is a different way to get there. This one's based on polar coordinates. You've got your r and your theta, and then you just go up. Now spherical is going to be a little different. So spherical, we'll have this angle theta still. This angle theta comes out here. This will be theta. But instead of having r, we'll have this, let's say this will come out like this. And we've got this angle phi. This angle will be an angle from the vertical axis. We'll just call it z again. And then this is sort of like the shadow down here. But this right here, this has a length of rho. So then this point here is going to be rho theta phi. So you go out theta, and then from the vertical axis you come down phi. These are just angle measurements, and then you come, this rho would get you out to that point. Okay, so that's something that many of you will see later. Okay, but what we need to do for section 10.3 is we need to be able to convert from polar to Cartesian and vice versa. And there's a technique we can use for these. So let's look first at converting from polar to Cartesian. All right, so let's say we're using the polar coordinate system. Let me try that again. All right, and we've got this point P out here. And the way we got there is we went theta degrees or radians. From standard position, we went out r units and we got there. And this is our theta. But what we want to do, we want to convert this to Cartesian. So we want this to be converted to xy. So what we can do is we can think, well, if we were to drop a line straight down here, this distance would be y and this distance would be x. And then if we look at this angle, so this distance here is r. Well, if we have a right triangle, this is the hypotenuse. So we could say sine of theta is opposite over hypotenuse. So just looking at that picture, we could say, okay, well, sine of theta is y over r. That implies that if we were to multiply both sides by r, we'd get y equals r times the sine of theta. And also, we could look at this and say, well, cosine of theta is x over r, because cosine of theta is adjacent over hypotenuse. So cosine of theta equals x over r. And that implies that x equals r times cosine of theta. Right, because I could multiply both sides of this equation by r to get here. Now, some of you who've taken physics, this will be sort of natural because you do something like this when you're working with like motion problems and things, or with vectors and forces. So this will be sort of natural if you're taking physics. But if not, it's just trigonometry, right? So then from here, we can use these equations. And the nice thing is when you convert from polar to Cartesian, Cartesian gives you a unique solution, right? There's going to be only one answer. So you get a unique answer here. So there's not a lot to worry about. We're going to get one answer. We just use these formulas here. We'll get our answer. Unlike polar's a little trickier because there's more than one answer. But when you convert from polar to Cartesian, it's very straightforward. You can just use these two formulas to figure out what x and y are, and you're good to go. So I guess we could say this. We could say if you are converting from polar coordinates, our theta will be equivalent to the Cartesian coordinates, our cosine theta, which is x, and then our sine theta, which is y. All right, so let's look at the other way. Let's look at, this time, converting from Cartesian to polar. Okay, now remember, the thing about polar is these are not unique. This is not going to give you a unique answer. And there's something else that makes these a little trickier too, which we'll talk about. But basically, if we started off, so we've got a Cartesian coordinate we're working with. So you've got this point P, and of course its coordinate is xy, which basically means that we've got this distance y and this distance x. So we want to convert this to polar. So we want instead for this to say r and theta. So what we do is we connect the line there to the dot, and we measure this angle theta. Okay, so to find this, keep in mind that we've got a right triangle here. We can definitely find this, right? Because Pythagorean theorem says that x squared plus y squared equals r squared right here, right? We'll call this r. So this r theta, this distance r, this distance r, so r is just going to be the square root of x squared plus y squared. Okay, so if we look at what we've got here, we can see r is the square root of x squared plus y squared. And then this angle theta, well, okay, I'm going to do this off to the side here. Isn't it true that tangent of theta equals y over x? So tangent of theta is y over x, just right triangle trig, right, opposite over adjacent. So if we wanted to get at this theta, how would we get rid of that tangent? We just want theta. Well, we could take the inverse tangent of each side, right? So if we take the inverse tangent of each side, then we'll get theta. Okay, so theta is equal to the inverse tangent, or the arctangent, right? It means the same thing, of y over x. All right, let me try to rewrite y. Okay, of y over x. Okay, so we've got these formulas, but we just have to be careful about one thing. This theta here, this is inverse tangent. So if you remember inverse tangent, okay, if you remember back to the days of trigonometry, when you're working with inverse sine, inverse cosine, inverse tangent, well, first what you have to do is you have to restrict the tangent function to force it to be 1-to-1 so that it has an inverse. And to do that, you would restrict tangent to be between negative pi over 2 and pi over 2. Okay, so that means that when you're using inverse tangent, if you ask your calculator to take the inverse tangent of a number, it's always going to give you answers in the first and the fourth quadrant, because it's going to go between negative pi over 2 and pi over 2. Inverse sine is the same thing. It'll be here and here. And remember, inverse cosine would be in these two quadrants. So what's going to happen is, if you are trying to convert a Cartesian coordinate to a polar coordinate, and you're in these two quadrants, and you use this, you're going to get the reference angle from these two quadrants. Okay, so you just have to be, just kind of keep that in mind when you use this. Okay, when you use this, the range of the inverse tangent function is going to be between negative pi over 2 and pi over 2, right? So this will always give us an answer on the calculator between negative pi over 2 and pi over 2. So it's fine if we're looking for points over here. But if we're looking for points over here, and it tells us like 28 degrees, well, that means that the reference angle, so if we got a point right here, we punch this in the calculator, it says 28 degrees. Let's talk about this reference angle. Here's 28 degrees. So we need to add 180 degrees to it, okay? So to fix that, just so you keep track of everything, when you're doing this, when you're converting from Cartesian to polar, draw a picture, right? I mean, when I say draw a picture, I just mean like draw a picture of your point so you know what quadrant you're in. Okay, so draw a picture to see what quadrant you are in. The quadrant the point is in. So I guess you don't really have to draw a picture, but what I'm saying is be careful. In case you're over in one of these quadrants, you have to just kind of be mindful of using the calculator, and it's going to give you some acute angle, right? It's going to give you some angle less than 90 degrees. So, okay. Also, of course, there's multiple answers for this because it's not a unique answer. So when we convert in this case, if we go like, say, from xy, if we convert, we're going to get r, which could be the square root of x squared plus y squared. And of course there's negatives too, right? So plus or minus, because you can have a positive r or a negative r. And then we'll get inverse tangent of y over x. Okay, so I'm squeezing that in there a little bit. Okay. So what we should do now is just try some of these and see how it goes. Okay, so let's try converting from polar coordinates to Cartesian coordinates. Remember, when you're converting to Cartesian coordinates, there's only one answer, right? So we don't have to be too concerned. So let me just make a little note here. There's only one possible answer. Okay, so generally it's easier to go in this direction. So let's look at, say, example number 1, which says we got this point 2 and 2 pi over 3. And just to make it a little easier, I'm just going to draw a picture of it just to see where we're at. Probably don't really have to, but we've got polar coordinates. The angle is 2 pi over 3, so starting from the standard position, we go over 2 pi over 3, which puts us up here. So we're going to be up here. This is 2 pi over 3. Then we go out 2 units, so let's just make this 1 and 2, so we are right there. Okay, so we want to find that. Well, we know we've got a couple conversions. X equals r times cosine of theta. Y equals r times sine of theta, which means that x equals 2 times the cosine of 2 pi over 3. And y equals 2 times the sine of 2 pi over 3. Well, if you remember from trig class or from pre-calc, when we're finding the cosine of 2 pi over 3, so what we do is we drop this down and we find the reference triangle, right? So if we want to find the cosine of 2 pi over 3, we drop this down, and we're going to find this reference angle, which is the angle right here, right? So if this is 2 pi over 3, that means this is pi over 3, right? It's a pi over 3. So if that's pi over 3, this is a special triangle because this side is 2. So think of the special triangles. If that's pi over 3, this is going to be pi over 6, right? It's pi over 6 here. This is pi over 3. So this would be the shortest side. So this would be 1. And then this other side would be the square root of 3. So this is the 30, 60, 90 special triangle, right? Pi over 3 here. It's the 60-degree angle. Pi over 6 here, 30-degree angle. And then this is the breakdown of the sides. So we also have to know about, if we're going to find the cosine of this, okay, so we're over here, so we need to know where is cosine positive. Well, there's the one memory hook that is sometimes shown. All students take calculus for the quadrants, meaning all the trig functions are positive here. Sine is positive here. Tangent is positive here. Cosine is positive here. Or the way that you could do, what I typically do is I just associate cosine with x values, with x coordinates. And it's just from using that, defining the trig functions cosine and sine from the unit circle. So I just associate cosine with x's. So cosine is going to be positive here. Associate sine with y values. So sine is going to be positive here. And then some of you were taught this way. When you think of this one, you kind of think of this one as being a negative one. You may have been taught that. Because really this point here, this point is the point -1 square root of 3. So some of you were taught, really for this, just do however you were taught. Some of you were taught to think of this one as a -1. And then when you do like cosine of this angle, you just go -1 adjacent over hypotenuse, so you get -1 over 2. Okay. However you were taught, just do it that way, whatever makes sense to you. But however you did it, you should end up getting -1/2 for this. So you get 2 times -1/2, which is -1. So x is -1. And then sine of 2 pi over 3. Again, we use the reference triangle here. We use this little reference angle here and use this triangle. So sine of 2 pi over 3 is going to be opposite over adjacent square root of 3 over 2. So we have 2 times the square root of 3 over 2, which then would cancel and give us the square root of 3. So the point here that corresponds to this point, if you use Cartesian coordinates, is -1 square root of 3. It corresponds to that. Okay, so hopefully this is making sense. That's just a lot of trig. There's a lot of trig in this section. Now let's try one more. Let's try this one. This one's a little different. This one is the point 4, -3 pi. And this one you can do a couple of ways. But let's first just plug right into here. And then I'll show you, just by looking at the picture of it, this one's kind of easy if you just look at the picture. But if we just plug in right from the start, x equals r cosine theta, we get x equals 4 times the cosine of -3 pi. Y equals 4 times the sine of -3 pi. Now we know the sine function is 0 at all integer multiples of pi. So this is just going to be 0. Now this other one, cosine of -3 pi, well, let's think of the cosine. So here's pi, -pi, -2 pi, -3 pi, and cosine, of course, goes something like this. Goes through all these integer multiples of pi over 2. So cosine of -3 pi is -1. So it's going to be 4 times -1, which will give us -4. So that means that this would give us the point -4, 0. And you can see it if you just go right from here. So think if you just drew, if you plotted that point with polar coordinates, and the angle is negative 3 pi, so it's negative, so I'm going, starting in standard position, I'm going in this direction. So here's negative 1 pi, negative 2 pi, negative 3 pi. So we're right back there. So we basically are just going like this. We're going, starting here, negative pi, negative 2 pi, negative 3 pi. So I'm on this branch. And then you go out 4 units. So I have like 1, 2, 3, 4. And it's this point right here. And then you can also see by looking just at this, yeah, that's the point negative 4, comma 0. Okay, so you could do that a couple of different ways. But you can always just use these formulas here, right? For converting to Cartesian. All right, but what about going the other way? So what about if we convert from Cartesian coordinates to polar coordinates? Okay. Now, a couple of things here. So first of all, remember, polar coordinates are not unique. So we can get different answers here, right? So these are not unique. And also, what the book will tell you for this part, this kind of homework, they're going to say, they're going to add to this. They'll say, so I'll just add to it too. So they're going to say where, so we'll say 1 with a positive r and 1 with a negative r. Right, so we're going to actually find 2 polar coordinates for each of these Cartesian coordinates. We're going to make one with the r greater than 0 and one with the r less than 0, right? Positive r, negative r. Okay, so here is the first point. We'll say number 1 is 1 negative square root of 3. Okay, so these are Cartesian coordinates. Well, all right, I'm just going to sketch this one. So let's see, x is 1, y is negative square root of 3, so it's going to be down here somewhere. So we basically have this is 1, and then this would be the length of it would be the square root of 3. So I'll put negative square root of 3 because that's a point. And then so what we're going to have to do is we'll make an angle coming from here, right? So if we wanted to get there, we'd have this angle theta. We have this distance r, right? We'd have to find this r. Well, formula for r, remember r equals the square root of x squared plus y squared. Well, here is x, here is y, so we could say r equals 1 squared plus negative square root of 3 squared. So equal to 1 plus 3, which is equal to the square root of 4 or 2. So r equals 2. So you can plug that 2 in. And then once you see this, you might even recognize this. This is a special triangle, right? 1 in this magnitude is the square root of 3, and this is 2. This is a special triangle that we were just talking about earlier. This is a 30, 60, 90, right? It's a 30, 60, 90 triangle. So there's a right angle here. So then this one, this is the shortest side, which means this is the smallest angle. So this is the 30 degree, or the pi over 6. And this is the pi over 3. So looking at this, we could see this is equal to r equals 2. And theta is going to be negative pi over 3. Right? Because we're going clockwise, so it's a negative angle, negative pi over 3. Okay, so we've got 2 negative pi over 3, but they also want one with negative r. Okay, so what if we go negative 2? Then what could I do? So if I'm going to go negative 2, it means I need to kind of like come out here somewhere, right? So I have to have this, this coming out in this direction. So it can come out in here and then go -2. Well, this is just a straight line here, so couldn't I just, whatever this is, add? So from here, this is 180, right? So if I take this angle and add 180, I'll get right there, right? So this angle is -pi/3. 180 degrees is pi radians. So if I add pi radians here, I get -pi/3 plus pi, which is 2pi/3. So this ends up being 2pi/3, which also makes sense. You can see if this is pi/3, this would be pi/3 here, which means this has to be 2pi/3. But that would give us a way to get a -r here, right? Just go 2pi/3. And this, since we're at it here, what if you wanted both of these to be positive? So I want r to be positive and I want my angle to be positive. Well, if I want that to happen, I could just start here and go all the way over here, right? This is pi/3 right here, and all the way around is 2pi. So this would be 2pi minus pi/3. Well, 2pi is like 6pi/3 minus pi/3 would be 5pi/3. So if I really wanted to, I could say 5pi/3, and then they're both positive. Okay, so there's lots of different ways we can write this answer. Once again, polar coordinates are not unique, so these are just 3. Okay, now this one happened to have a special triangle, but sometimes they won't. So let's try this number 2 here. Number 2, let's say this one is the point 3, 4. Okay, so if we draw this one out here, x is 3, y is 4. Got this point right here. All right, so what we want to do, of course, is find theta and find r. Well, this is 4 and this is 3. So we've got a right triangle. So what that means is some of you will know what this is without really doing any math at all, because you've seen this before. This is a right triangle, and this is a Pythagorean triple, right? It's a 3, 4, 5 right triangle. If this is 3 and this is 4, that's going to be 5 from the Pythagorean theorem. It's just one that's kind of well known. But you could use this formula, of course, x squared plus y squared. And you would get 3 squared, which is 9, plus 4 squared, which is 16, which gives us the square root of 25, which is 5. Okay. So r is 5. Now here, though, here's going to be the difference between this problem and this problem. This is a special triangle where theta is a nice answer. This is not a special triangle. So if we want the exact answer, we're going to have to do this. Theta, in this case, looking at this, theta is just going to be the inverse tangent of 4/3. That's the exact answer. If I put it in the calculator and get a decimal approximation, it's just going to be kind of a messy looking answer. So if you want the exact answer, we could say, okay, this thing is equal to 5 and then inverse tangent 4/3. So if the book were to ask for a decimal approximation or just an approximation of the polar coordinates, we could just punch this in the calculator and get some decimal answer. But if they want the exact answer, I said this is the exact answer. Now they are going to want this with a -5 also. So how do we figure that out? So if I have a -5, it means I need to come over here somewhere, right? So it's like I'd have to extend this thing out here. So you could think of it as, well, what if we just came out here? Well, that's basically this angle theta plus pi, right? Or this angle theta plus 180 degrees to get a straight line. So whatever this is, if I add pi to it, it'll be on here, and I'll be on this line. And then if I go -5, I'll get back here. So whatever theta is, I need to add pi to it. And what's theta? Well, theta is this. So basically, I'm going to have pi plus the inverse tangent of 4 over 3. So it gets a little messy if they want the exact values, but that's what we could do. You could just add pi onto this to have this angle here, right? This angle here, which give us this line. Then we go back 5, negative 5 to get back there. So now let's take a look at some special polar graphs. Okay, example number 1 is r equals 4. So when you see something like r equals 4, what it's basically saying is it doesn't matter what theta is, r is always going to be 4. So let's see, let me get this plotted out here. So it means if theta could be pi over 4, r is still 4. Theta could be 0, r is 4. So basically you're going to end up getting a circle here, right? So you get this circle that goes through at 4. And of course I'm doing it by hand, so the circle is not going to be so good looking, but hopefully, oh my god, this is a horrible circle. Okay, hopefully yours on your notes looks better. But basically it's saying it doesn't matter what theta is, r is always 4. This is sort of like the equivalent of if we were using Cartesian coordinates and we said y equals 3. It's just a horizontal line, right? This is saying it doesn't matter what x is, y is 3. X could be 1, y would be 3. X could be negative 7, y is 3. It doesn't matter what x is. Same thing here. And also, incidentally, drawing lines is typically easier with the Cartesian coordinates, whereas drawing circles is typically easier with polar coordinates, polar graphs. So r equals 4 is super easy, just a circle with a radius 4 centered at the origin. And you could try this on the calculator also. When we use the calculator, this time you have to go to the mode button and go to polar mode. So when you go to mode, so most of the semester we've been in function mode. Section 10.2, 10.1 and 10.2 actually, we started using parametric mode, and then in 10.3 we want to go to polar mode. Notice if you do that, if you change your graph to polar mode, then you go to y equals, it says r1 equals, r2 equals, r3 equals. So in polar mode, we don't use t anymore like we did in parametric mode. We don't use x anymore like we did in function mode. Now we use theta. So when you press the button on on your TI-83 or 84 that says xt theta n, and you're in polar mode, it's going to be theta that shows up. And when you press y equals to see your graphs, it's going to say r1 equals. Okay, so you could, on your graphing calculator, pretty easy to punch this in there in polar mode, press r sub 1 equals 4 and hit graph, and you'll get a circle. Although you may have to go to your window to square it, or easier just hit the zoom, press the zoom button, zoom square to get a nice circle here, okay? Okay, here's another one. Theta equals pi over 3. Now this one we can't graph on the calculator because it's not solved for r. This would be sort of like trying to graph x equals 3 on the calculator. In function mode, the graph x equals 3 won't show up, right? Because in function mode it says the calculator is going to ask you for y. So x equals 3 is a vertical line. So theta equals 3. It's easy enough to graph by hand, because basically this is saying it doesn't matter what r is, theta is always pi over 3. So theta is just pi over 3 no matter what. So this graph is just going to be pi over 3 going like this, right? That's just regardless of what r is, theta is always pi over 3. So this is what it looks like. And let's see. Okay, so we got a couple there. And then you'll see some like this too. So sometimes the homework will ask you to do something like this, where we'll say this is problem number 3. It says that r is greater than or equal to 1 and less than 3. And also, it tells us about theta. Theta is in between negative pi over 4 and pi over 4. So if we were to graph this one, all right, well, first I'm going to take care of this theta. Theta is between negative pi over 4 and pi over 4. So here is negative pi over 4. Here's pi over 4. We know, so theta is in between here. So we don't care about out here. Theta is in between here. And then r is between 1 and 3. So let's say this is 1, 2, 3. So r is greater than or equal to 1. So r goes like this, right? Greater than or equal to 1. But it says it's strictly less than 3. So at 3, how we show that is we have a dotted line at 3. So the solid line shows that 1 is included here. R is greater than or equal to 1. So this is 1, 2, 3. So it's greater than or equal to 1. So you have a solid line here. But if it's strictly less than 3, it never quite gets to 3. Let me just mark these. This is 1, 2, 3. So the way we show that is a shaded line. But then also all of this, or a dotted line, sorry. All of this has to be shaded. So all of this is included in this picture. So it's a little bit tough to show, but all of this would be shaded in. So the picture would be all of this in here. Okay, so some of them are a little tricky to draw, but that's what they're looking for. Now on the homework on this one, you see on the homework sheet, if you look at this section, homework sheet for the last 2 problems, I think it's like 61 and 63. No, 61 and 62. On the homework sheet, it says use your graphing calculator. So in the old calculus edition, it said that in the homework also, but for whatever reason, the 9th edition doesn't say that in the book. But you don't want to try to draw 61 and 62 by hand, okay? So I think they just left that off for some reason. But you definitely, when you're working on the homework 61 and 62, you want to put your calculator in polar mode and press the Y equals button and use that. And I'll tell you, number 62, you're going to want to use that one on Valentine's Day for your special someone. You'll thank me later. So try that one on the calculator, though. Don't try it by hand. So, okay. So those are some unusual ones, or a little bit different ones that I have us do. There'll also be some that we should be able to do by hand. So let's take a look at one where we can do by hand or on the calculator. The calculator works too, but let's look at this example where they will say something like this. Sketch the curve and it has a polar equation. So it has a polar equation of r equals 2 sine theta. So what we want to do, something like this, is make a t-table for theta. And then r, which is 2 times the sine of theta. Okay, now I typically don't need this many points, but I do for this one. So I'm going to go with 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And there's a whole bunch of trig practice here. So you just want to figure out, I'm going to plug in 0 for theta. So this is kind of an easy one. Sine of 0 is 0. So this is going to give us 0. If you plug in pi over 6, sine of pi over 6 is 1/2. So 2 times 1/2 is just 1. So just for some practice, you should press pause and go through and fill these out and see what you get, and then I'll show you what to do with that. So, all right, hopefully you guys figured these out. And this is going to be 1 over the square root of 2. This is going to be the square root of 3. And then we've got 2. And I'm going to just put something here. This is roughly, roughly 1.4. This is roughly 1.7. And then let's see, 2 pi over 3 would give us the square root of 3. This would give us the square root of 2. This would give us 1. This would give us 0. All right, so the way we do this is you're going to make this graph. And I don't know if you've ever seen polar graph paper. I haven't seen it in a while, but I've seen it before. And it does something like this. It will have these markings on it. So it'll have like pi over 4 coming out here. And it'll have the equivalent thing on, in each of the quadrants. And they'll have something like this for pi over 6. One like this for pi over 3. And likewise over here. Oh, these are hard to draw by hand. So not gonna be very pretty, but oh my gosh. Okay, so they'll have something like this, but then they'll also have these circles on here, like here's 1 and here's 2. You have 1 and 2. They'll have these circles in here, and they'll usually kind of be lightly drawn in here, so you can draw things on here. All right, and then the way we would do this is we just start here. So when theta is 0, r is 0. Okay, so if theta is 0, r is 0, so we're right here. Whoops, I don't want that color. Theta is 0, r is 0. And then when theta is pi over 6, so theta is pi over 6, now r is 1, so I'm right here. Okay. When theta is pi over 4, I'm around 1.4, so I'm out here a little bit. And then when we're at pi over 3, we're at 1.7. By the time we're at pi over 2, we're up here at 2. And then you just keep on going here. My drawing is unfortunately not the greatest at all. but it shows that what we do when we draw this is if this picture, if these were drawn correctly, we would end up getting a nice circle. And if you go into polar mode and go to y equals and plug this in, you get a nice circle. Now remember, to get it looking like a circle, you have to play with the window a little bit. So you may have to go to your window, hit zoom, square. Another thing you may have to do if it's too choppy, if you go to the window button, and it's going to say something like on the window, you'll have some marks here. So you'll have things like theta min, theta max, and theta step. This is a lot like parametric equations, a lot like it. So sometimes you have to adjust these. Theta step, if it's too choppy, I usually just, for this, I put pi divided by 180. Then it will usually smooth it out. Okay, this is a lot like parametric mode. Okay, so if you punch this in there, you should get a nice circle right here. It'll have, it'll be centered here, it'll be like sitting on the origin here. It'll have a radius of 1. And it'll look something like this, but it'll be a real circle. Okay, so there'll be some of them in the book where they want us to do this by hand, and a lot of times it just comes down to some trig or some algebra, and then plotting some points. You can always check it by just using your calculator. Okay, we've got two more things and we will be all set. And they're related. So we have to be able to convert Cartesian equations to polar equations. So if we have a Cartesian equation like y equals x plus 1, and we want to convert this to polar equations, we just go back to what we've already learned. So we know already that x equals r cosine theta and y equals r sine theta. So we can use that right here. So this is an equation of a line, y equals x plus 1, right? We know what this looks like. It's got a y-intercept of 1 and a slope of 1. Pretty basic. If you wanted to do this in polar equations, which usually is not as good, Cartesian equations are usually better for lines. Polar equations are usually better for circles. So this is probably going to be better as is. But if you wanted to convert it to polar, we use these. So to convert it, we would say, okay, so y, that is r sine theta, equals x, which is r cosine theta, plus 1. And then what we have to do, instead of solving for y, like here we have to solve for r. So to solve for r, I need to get the r's on both sides of the equation. So I'm going to subtract this from each side, which would then give us r sine theta minus r cosine theta equals 1. Once we have these on the same side, we can factor out an r. So you factor out an r and we get sine theta minus cosine theta equals 1. Then, of course, I divide. So I'm going to get r equals 1 divided by sine theta minus cosine theta, which is kind of an ugly way to say this, right? So this should be a line. Now, just to let you know what could happen. So if I were to graph this line in function mode, it's going to just be a line that goes like this, and it'll be just fine, right? Now, if I do the same thing over here, what could happen, remember, if I don't have the theta set right, maybe you graph it and it goes like this, and you're like, well, that's weird. Where'd the rest of it go? Well, it's just when you set your theta to minimum and maximum, maybe it didn't get everything. So you just have to tweak it a little bit, and then it'll get the rest of it, okay? But again, it's just not as convenient trying to graph a line with polar equations. But this would be the equivalent way to do it. Or I mean, the equivalent way to write this this line. Okay, here's kind of a little bit nicer one. Let's say we had x squared plus y squared equals 1. Well, we know what this one looks like. We've seen this plenty of times, Cartesian equation. Now, of course, if you wanted to graph this on the graphing calculator, you have to solve it for y, and you graph it in 2 parts, right? But we know enough about circles to know this is going to be a circle centered at the origin with a radius 1. So let's see what it looks like if we put it in polar coordinates. So x is r cosine theta. We have to square that. Y is r sine theta, so we square that. That gets 1. Then right here we've got 2 things squared. So we're going to use that rule you learned a long time ago in algebra. A times b to the m is a to the m, b to the m. So we'll do that here. So we'll get r squared times cosine squared theta plus r squared times sine squared theta equals 1. Another thing you'll notice, cosine squared theta is how we typically write it. But remember what cosine squared theta means. Cosine squared theta really means cosine of theta squared. Okay, so just keep that in mind. But now over here, we could factor out an r squared, right? So we could factor out this r squared, and we get cosine squared theta plus sine squared theta equals 1. Now think back, have you ever seen cosine squared plus sine squared? I think you probably have, right? cosine squared plus sine squared is just 1. So this says r squared equals 1. If you take the square root, you'll get r equals 1. Now you might say, what about r equals negative 1? Well, you could do that one too. These are going to give you the same thing, right? Because basically this is saying it doesn't matter what theta is, r is always 1. So this is going to be a circle of radius 1 center at the origin. This will be the same thing. Remember, you can have a positive r or a negative r. So usually people write it like this with a positive one, but you could write it like this also if you wanted to. Okay, so that is going from Cartesian equations to polar equations. Also, sometimes they'll ask us to go in the other direction. Okay, so let's take a look at a couple of those. All right, so let's say, I'm going to convert the other way now. Let's say we have r cosine theta equals 2. Well, r cosine theta equals 2. Well, r cosine theta is just x. So this is like saying x equals 2. Right? So this is just x equals 2. This is a vertical line, right? So r cosine theta equals 2 is a vertical line, x equals 2. What if we had, let me just make another kind of strange, easy one like this. We'll call this one 1.5 because it's very closely related. What if we had r sine theta equals 5? Well, r sine theta is just y. That's just y equals 5, horizontal line, right? Okay. So you can't graph this one in polar or in Cartesian coordinates because it's not a function, right? X equals 2. You could in polar, though. You just have to solve this for r. So if you graph in polar, r equals 2 divided by cosine theta, then you'll get the vertical line, x equals 2. Okay, what about, okay, here's a very, very strange one. We'll call this one problem number 2. R sine theta equals the natural log of r plus the natural log of cosine theta, and we want to write this with a Cartesian equation. So y's and x's, right? Not r's and thetas. Cartesian, we want y's and x's. Well, for this one, what we're going to want to do is remember a rule of logarithms. So remember logarithms, or log to any base, but since this is a natural log, I'll use natural logs. Logarithms have a way of simplifying mathematical operations. So instead of multiplying, if we wanted to, we could add, which is simpler. Instead of dividing with logarithms, we could just subtract, which is simpler. Instead of exponentiation with logarithms, we could multiply, which is simpler. But for us, for this problem, let's use this first one. We've got this condition here, so I'm going to just move it over here. We go the opposite direction. Okay, so I'm going to say, well, r sine theta equals, this is just the natural log of r times cosine theta, right? We're just going in this direction backward. We're multiplying these two inputs together. Natural log of r cosine theta. And well, r sine theta, that's just y. Because natural log of r cosine theta is just x. So with Cartesian equations, this just says y equals natural log of x. Okay, so I think you've seen all you need to see for 10.3. It's a pretty decent introduction to polar coordinates. So go ahead and give that one a try. And as always, just let me know if you have any questions.